Hello, my name is Sarp Coşkun. Let's quickly talk about what is a deep neural network. The neural part is coming from the past where we thought these networks are mimicking how human brain works. But we don't know how human brain works. Let's put this on the side. And let's also come back to the deep part later. Let's talk about what is a network. These networks are family of functions. So what is a function? I will put an input here, let's call it x, and then we have an output y. And then I can represent a relationship between these two. And if we do a linear function, let's say phi x plus theta, that can represent the output. This is a linear function. You can assume the phi is the slope and theta is the intercept of this function. And these two are called parameters. Okay, this is a simple linear function. You can assume this will come up with a result, something like this or this, and it will be a straight line. But let's assume we would like to represent a more complex structure where we can solve, let's say, this problem on the right-hand side. I'm going to draw a very simple question here. Let's assume we're going to find the child height. This is the height, this is the age, and there will be a relationship which is not linear. It's a nonlinear relationship. So let's say something like this. And in order to represent this, we need to have a nonlinearity in our solution. For that, I will add another sample here. Let's say in the middle we call it h, which is our hidden layer, which we will enable through an activation function, which is nonlinear, and then our output. So within h, what we will do, we will pass this parameters, and then we'll call an activation function. This can be any nonlinear function. A very common one is ReLU, which is a rectified linear unit, and we will pass these into this activation function. So the output will be in this scenario. Let's put the parameters. We have a phi 0. Let's call it, this is phi 1. And we will have a bias term here. That will be, let's say, theta 0. And then there will be another bias term here from the hidden layer. And let's call it theta 1. So if we add these up, what will happen in the activation function, I'll represent like this, phi 0 times the input plus our theta 0. Okay, and then this will be passed to our activation function, and then we will multiply this with phi 1, and we will add our theta 1, which is our bias, and then that will be representing the output. So this will result in a nonlinear function. We can call it like a piecewise nonlinear function. So let's say it goes like this, and then another linear result. So in here, do you see a joint? This is because of the hidden unit we have in the network we built here. So in here, we have 4 parameters, 1, 2, 3, and 4. So you can increase the amount of hidden units in your hidden layer. So I'll put here input layer, hidden layer, and output layer. So within these layers, you can have multiple inputs, and you can have multiple hidden units, and you can have multiple outputs. And if there's only one hidden layer, as you can see here, we call it a shallow neural network, and the width of this represents the depth of our network. If you have more than one hidden layers, we call them deep neural networks. All right, this is a very high-level explanation. Let's dive deep into how each component works and discuss the loss function.